All right, this is Unit 2 for Math 2. It's actually Algebra 1, Unit 6 from the illustrative math curriculum, but we do integrated math at Coastal Academy High School. And this lesson is the first lesson called A Different Kind of Change. So in this lesson, we looked at the relationship between the side lengths and the area of a rectangle when the perimeter is unchanged. If a rectangle has a perimeter of 40 inches, we can represent the possible lengths and widths as shown in the table. We know that twice the length and twice the width must equal 40 because there's two lengths and two widths to go around the outside, and perimeter is just the distance around the outside of a figure. Which means that the length plus the width must equal 20 because one of the lengths and one of the widths only gets you halfway around, so half of 40 is 20. Now, if we were to take that relationship between the length and the width and we were to graph it, we could rewrite it like this and then graph it like this. The relationship between the length and the width is linear because it makes a straight line. However, what we talked about in this lesson was the area of the rectangle with perimeter of 40 inches. So here's possible areas of different rectangles whose perimeter are all 40 inches. Remember, the relationship between length, width, and area for a rectangle is the length times width equals the area. So 2 times 18 equals 36, 5 times 15 is equal to 75, 10 times 10 is equal to 100. And here is a graph of those lengths and areas from the table. Now this looks different than what we've seen before. What we've seen before is linear equations, and actually we've even seen exponential equations, but this one does something different. It's not exponential, and it's not linear. Notice that initially, as the length of the rectangle increases, the area also increases. However, we hit a point right here where as the length keeps getting bigger, our areas start to get smaller again. We haven't studied relationships like this yet, and we will investigate them further in this unit. So let's take a look at the cooldown. 100 meters of fencing. The table shows some possible values for the length and width of the yard. Well, remember, the relationship between length and width and area is that length times width equals the area. Now you might be wondering, down here I don't have the width or the area, but remember, if the length is 40, well, this would also be 40. Total distance around the outside of this thing should be 100. So what does the width have to be? If the values for the length and area are plotted, what would the graph look like? Well, if you have to, plot it. See what it looks like. But you've already seen an example. How is the relationship between the length and the area of the rectangle different from other kinds of relationships we've seen before? So quick reminder, linear, exponential. That's what you should have seen in Math 1 or earlier in Algebra 1. I hope this is helpful. If you have any questions, let me know.